Let's resume then our technical talk. So after the discussion and the keynote speech, we're now going to resume the scientific paper talks, and this session will be mainly revolve around neural machine translation. And I would like to invite Marcin as our first speaker, presenting his work on neural machine translation and how he compared and evaluated his neural machine translation ready for deployment, his case study on 30 translation directions.
Thank you very much. This is joint work with Thomas Streuert, my PhD student, and Hugh Huang. We basically started this work, by trying to see, by realizing that although we have been using neural machine translation for a while during the shared tasks already, at least for more than a year, and although a lot of press coverage is happening in the very domain specific news portals and blogs, neural machine translation has not really arrived yet to the smaller companies and smaller entities. For instance, Google, Sysrun, and Microsoft have announced and deployed it. But if you only look at, for instance, what was happening at AMTA this year, within the user section and the government section, there wasn't a single paper on neural machine translation. Well, there weren't actually that many papers on neural machine translation in the research track either, but at least there were some. And I think whenever, also when you look back a little bit, in the user sections, no neural machine translation across the lesser conferences. Sorry? Oh no, I mean, right now I just meant with reference to this time. I'm not saying that there wasn't any neural machine translation before. That is over-interpretation. The question is, okay, so what about it? Well, what's the problem? Is it not accessible? Is the quality not high enough? Are the toolkits not out there? And we took a look at the United Nations corpus, because this is a corpus which is actually being used for in-house training of the translation system at the United Nations. I'm collaborating with the United Nations. It contains human translated documents from 25 years across the 6 official United Nations languages, and has a very interesting subcorpus that is fully aligned across the 6 languages. So we can do the full translation matrix on this sub-aligned corpus. We have a test set, which is also sub-aligned across those 6 languages. And this would give us a very comparable translation results across all possible directions. The corpus is quite big. Even this fully sub-aligned corpus is more than 11 million segments, more than 300 million English tokens. So this should be an interesting use case for fully in-domain neural machine translation compared to the general domain which we are trying to do, because TED Talks can be about anything. The WMT news task can be about anything. LSPs and in-house machine translations had quite good experience with Moses and phrase-based systems, especially when they built highly customized in-domain systems. So the question is, maybe the pain for switching currently is too big. Maybe the systems are actually pretty good. I mean, we just saw that for some areas, phrase-based still beats the neural machine translation thing. So maybe something like this is happening. How we preprocess the corpus. So sentence longer than 100 words were discarded. This is actually not that uncommon in United Nations data. We lowercase data as it was done in previous work. So we are reusing the phrase-based system that have been created. And this is also, the systems are also lowercased in the in-house systems at the United Nations. We use the Moses tokenizer for most of the languages. For Chinese, we also add JIBA before that. So we first segment into Chinese tokens, and then we run the English tokenizer on top of that, just to make sure that any surviving English words which might be in the Chinese corpus get also tokenized. We didn't do anything special for Arabic, so no specific preprocessing there, apart from tokenization with the English tokenizer, which is maybe not that great, but since punctuation in Arabic are not that difficult. There aren't any abbreviations really, and it wasn't much of a problem. And we used BP subword units for the neural machine translation models with 30,000 units in the source language and another 30,000 units in the target language. The choice, why 30,000? It turns out that the vocabulary in the United Nations corpus is not that diverse. So if you stick to this number, it actually hardly ever segments a word. So you can go 10 or 20 sentences without a segmentation occurring with this quite small number of units, actually. The interesting part here is that we have already Moses results for all 30 language directions on the 6-way corpus. This is from joint work that was presented at LREC. And the current system is the actual system that is being used in-house at the United Nations. So they're using a Moses configuration, which is being trained with MGISA++. The word alignment is running 5 times model 1, 5 times the HM model. They're not going higher to model 3 or model 4. There is a 5-gram language model trained only on the target parallel data, so no additional monolingual data, because basically everything there is being translated. So if it's there, it has been translated. There's no additional monolingual data. The default lexical reordering model, which you get when you use the train Moses script. 5-gram operation sequence model, so it makes it kind of similar to the Arabic setup you guys were fighting. A 9-gram word class language model on top of that. The word classes were produced with word2vec. And the phrase tables are significance pruned. This is mainly for speed. As far as I'm aware, in terms of quality, that didn't make much of a difference. So quite equivalent to just not pruning. But I think 5 or 10-fold speed up compared to not pruning. And for decoding, the cube pruning algorithm with a stack size and cube pruning pop limits of 1,000. This is again chosen for rather fast translation speed. Translation quality might suffer a bit, but these are probably fractions of blur points. The neural translation system that we used. This is again just the WMT configuration with slight changes. We have a slightly smaller mini batch size than during WMT because of the sentence length. We clipped the gradient to norm 1. We trained with ALA delta at this point, while by now we have switched to Adam. But this work started somewhere in, I think, June, which was actually before we had reasonably working constants and hyperparameters for Adam. We trained first for 1.2 mini batches, 1.2 million mini batches, and saved checkpoints every 30,000 mini batches. The last 4 models, or last 4 checkpoints, were used for assembling. And we trained for 4 epochs, roughly 8 days on NVIDIA GTX 1080, so this is gamer hardware. And in total, for all 30 directions, this took around 320 days of computation time on up to 16 GPUs over roughly 3 months. The GPUs, again, during about half the duration, we were only using the GTX 1080s. Before that, the landscape of GPUs was a little bit more diverse. We've been using GTX 960s, the older Amazon GPUs. I think they've been switched now to something much better. So if we only had used those GTX 1080s, it might have been probably a little bit short, but not much. 30 language directions with 8 days still takes its time. Results. Just an overview. We'll go through the languages one by one. Out of Arabic, blue is phrase-based, so this is quite complicated phrase-based system. And here we see neural. I guess this kind of confirms the results that you guys had, especially since the phrase-based setup is actually quite similar. I think even bigger differences than you had, because you had something around 1 blur point, if I'm not wrong. A bit more than 1, yeah. For the United Nations corpus, for out of Arabic, we see nearly 2 to 3 blur points for every language pair, apart from Chinese. So whenever we translate into Chinese or out of Chinese, we are going to see big jumps. So Arabic Chinese is 8 blur points at this point, after training for 8 days. Out of English, again, the neural system generally better. with 3 between 1 and 3 blue points. And of course, again, the big jump for Chinese, nearly 9 blue points, or 9 blue points actually. Also into Russian, interestingly, 2 blue points over the phrase-based system. Out of Spanish, a similar picture, although the differences are smaller, apart from Chinese again. And parity for English-French, Spanish-French at this point. Out of French, the only time we actually see a phrase-based system that beats the neural system, although the difference is very small. And we also see that the differences between the phrase-based and the neural systems are a lot smaller, somehow for translating out of French. I don't know why. I would have expected the picture to be more similar for translating out of English or out of Spanish. And again, of course, Chinese, big difference. Out of Russian, Arabic, interestingly. So translating out of a morphologically complex language into a morphologically complex language, and we get quite a big improvement here. I'm not quite sure whether this is not only due to using BPEs, actually. Because the phrase-based system at this point might be at a disadvantage because it doesn't have BPEs, and the neural system does have BPEs. So we should probably do a kind of contrastive experiment here. What happens if the phrase-based system gets BPEs? I actually know out of experience that if you do Russian translation with BPEs, you get nearly a blue point. That might explain the difference away at this point. Russian Chinese, again, huge jump. Out of Chinese, well, the same picture as before. Whenever we have an Asian language in this, the distance is very, very big. And this graph kind of sparked a question, okay, whenever there's Chinese, the difference is huge. So what about hierarchical machine translation? Since hierarchical machine translation is supposed to be pretty good when working with Asian languages, with Chinese, when translating out of Chinese into English. So we did that experiment as well. First out of, on 10 language pairs actually, because the main working language pairs at the United Nations are out of English and into English. So out of English, when we do Hiero, the picture is mixed with the expected exemption, it would be English-Chinese. So here we have quite a big jump. Compared to the neural, though, not really. So out of Chinese, into Chinese with neural, much better than with hierarchical, despite a quite impressive jump with hierarchical, which I think is kind of a little bit tragic, because finally you got hierarchical working, and now neural comes around, and it's kind of over again. And then we also checked for those main languages, what happens if we keep training a little bit longer. For me personally, training roughly a week is a kind of point of pain. If I have to train longer than that, I get nervous. But apparently for neural, it still makes sense. You can kind of press up to 1 blur point out of it, at least for out of English. So it might be worth it, especially for English-Chinese, where the gap is bigger anyway. It might be a thing, although we noticed that it starts flattening quite quickly. So maybe you do not need to train for 16 days. Maybe it's enough to train for 10 days for this particular setup at least. Into English, again, interestingly, hierarchical better into English than any phrase-based system, which seems to be a United Nations corpus oddity, because I cannot remember any WMT where hierarchical would have beaten the phrase-based systems. Has this ever happened? It has happened. Okay, I don't know. Neural, mixed. So French English, the neural systems, Russian English, the neural systems are actually worse than hierarchical, unless we train a bit longer. So if we keep training, the neural systems are able to either surpass hierarchical or come a good deal closer. So we are 0.4 blue points below the hierarchical system at this point. I guess among 10 language pairs that this one loser would be acceptable, since it's still 1 blue point better than the phrase-based system that is actually being used in-house. So it doesn't seem to be a quality problem, at least for this 30 language pairs and for this particular in-domain corpus. You could switch to neural MT, losing 0.4 blues for Russian English and gaining on anything else up to 10 blue points for out of Chinese and into Chinese, which seems to make it worthwhile. So is there a translation speed problem? Because I'm not quite sure what the United Nations would think if I told them you should buy GPUs. But can you run it on CPUs? You can now. So there's the MUMT Toolkit, which at that point is a NeuroMT implementation developed purely in C++. At that point, it's only a decoder, so there's only inference, but we'll be working on making this more flexible. It's supposed to be fully compatible with Nematus, and it also should produce nearly exactly the same results during translation. There may be some small differences. 3 out of 1,000 sentences might be different because of numeric precision things. But apart from that, you should usually get the same translation quality. Multi-GPU support, multi-CPU support. You can mix GPU, CPU support with sentence-wise threads. There's low latency CPU-based decoding with intra-sentence multi-threading, so you can use multiple threads to translate one sentence. Or you can distribute multiple sentences across multiple threads. Assembling is enabled, vocabulary selection, so you can reduce the time in the final output layer. Integrated segmentation with subwords, so no preprocessing with pesky Python scripts. You just pass the subword units into the configuration file, and segmentation happens on the fly, which in my opinion is a good thing because this BPE segmentation is so specific to the neural stuff that it should be, in a server setting, for instance, it should be a model internal thing. Checkpoint assembling and averaging. This is a little bit problematic because if what we are seeing is that when we are assembling the last 4 checkpoints, we are getting an improvement of nearly 2 blue points, 1.6 blue points. But we are losing translation speed, WPS is words per second, which is natural. It's going to be at least 4 times slower because we are scoring 4 times. And memory is going up. And a little trick I discovered half a year ago, you can actually average those models. You can take the models and average them parameter-wise, per matrix and per parameter, and you get results which are nearly on par with the checkpoint ensemble. Translation speed stays the same, memory stays the same as the single model, and you can go on averaging, so you can average 8 models instead of 4. And at that point, the quality reaches the quality of the last 4 ensembles. This also works with Adam, interestingly. So this is not an ADA delta specific phenomenon, and it seems to work always. So basically, whenever, I would just say, just do that. Even if you are training systems across multiple training runs, you can then just assemble those together. And instead of having to do, I don't know, a 16 ensemble, you can do a 4 ensemble with average systems. Of course, this will not work across models from different training runs. So do not try to average models that came from different initializations. This is not going to work. I actually tried that. So what happens is it just totally gobbles up the model. The output is random, weird stuff. Okay. What else? Vocabulary selection. Decoding time on the CPU is dominated by the final output layer. So we have 30,000 vocabulary items. There's a softmax happening over those 30,000 vocabulary items. There's a big matrix multiplication happening. And this takes up nearly 80% of decoding time if we do not do anything with that. Already in 2015, Jean et al. Proposed to clip per sentence vocabulary to the 30,000 most common words out of a huge vocabulary of 50,000 items, and to the 10 most probable translations for each source word. They were using word alignment for that. Later we found, and similar things have been found by me et al., that you can actually reduce the number of most common words and in favor of increasing the number of most probable translations, and it doesn't hurt quality at all. This results in average on a vocabulary size per sentence of around 1,300, 1,250 vocabulary items. So this matrix multiplication gets nearly thrown out of the time. So what's left by now is now really going through the GAUs and the encoding, and not so much the final encoding layer anymore. The blue scores remain roughly the same, although the translations change a little bit. So you might get slightly different translations with exactly the same blue scores. Speed and quality versus beam size. So what type of beam size would you choose for a deployment setting? This is quality, blur. So we are seeing that even with a beam size of around, With a beam size of around 10, there's basically no quality gain anymore. Even with 5, the loss is, I think, 0.1 something bleu. And then we plotted the speed against that and decided to go with a beam size of 5 because this is the last point before the big drop. And this plot for speed looks very weird. You would kind of expect something smoother, basically an inversion of the bleu curve. But what's happening here are Kubla's kernel switches. So we have so optimized the decoder so far that the performance is not dependent anymore on what we are doing, but what is happening in the matrix multiplication. And apparently there's a problem in the matrix multiplication algorithm on the GPU that it switches to non-optimal kernels for certain batch sizes or kernel sizes and matrix sizes. In my opinion, that's something of a bug. Unfortunately, not ours, so we cannot fix that. Exactly the same thing, exactly the same valley. And the weirdest thing is that the beam size of 12 is slower than the beam size of 20. And we actually we profiled that. We could see in the NVIDIA graphical profiler that this is exactly where the kernels in the GPU start switching, that we are seeing this kind of phenomenon. One solution might be maybe to look at a different multiplication library. I think there's Nirvana around, which is supposed to be a lot smoother. So whenever they compare how the kernel switches look like, so Nirvana has a nice curve, while Kubla's does something like this for different matrix sizes. And I guess this is the effect in actual application. I was even thinking about doing a secret feature that when someone enables beam size 10, I just switch to beam size 20 automatically because it's going to be faster. But I don't know, maybe people will get upset when I do that. Okay, translation speed in terms of words per second. What has been reported in literature? Google on its TPUs, for instance, said that they seem to be fine with 350 or 360 words per second for their enormously huge models. So we cannot compare model complexity at this point, but just that they reported, okay, with this speed, we seem to be okay. The speed with the in-house Moses setup on 16 CPUs is 450 words per second, so kind of comparable. And now if we take a look how Nematus on the CPU is doing, the Theano implementation, and on the GPU, not so great. So on the CPU, at least 10 times slower would probably be unacceptable. On a GPU, I'd say same ballpark. Even if we are roughly 2 times slower, it's probably not much of a problem. McDuff Hughes from Google Translate was recently in Edinburgh, and he said that you could go 3 times slower without people complaining. So being 2 times slower might not be a big thing, but it would incur hardware costs. People would need to buy several GPUs to install them and maintain them with, if you have any idea what convincing IT people at the UN to accept non-standard hardware is, there's a much higher cost than the hardware cost actually involved in that. CPU with MUMT, without vocabulary filtering, 140 words per second, with vocabulary filtering, 270 words per second. So with a 16-core CPU, we can match the performance of a GPU with Nematus. And we are not even 2 times slower than Moses. So this is the point where I would say we can totally deploy that without people probably complaining too much. If it was possible to use GPUs with MUMT, we would have something like this. So a pure C++ implementation with vocabulary filtering is more than 4 times faster than the Theano-based version. Latency. Recently, by latency, we would measure how long it takes to produce a single sentence. So not in a multi-CPU or multi-GPU setting, but really we submit a sentence and how fast can we get the response for a single sentence. This question is interesting if you want to do, for instance, predictive translation. Because there's just no way you can take advantage out of multi-threading at this point, or out of sending different sentences to different threads. So latency at this point. Moses CPU, 700 milliseconds. Nematus CPU is not listed here because it was somewhere around 8,000, and I would have a problem with the graph at this point. So Nematus GPU is slightly better than Moses in terms of latency. MUMT CPU, without vocabulary filtering, 2 times slower. With vocabulary filtering, not that much slower, so that would probably be acceptable if the Moses speed is acceptable. And the GPU version. which is very nice in my opinion. So if you want to do predictive translation, you probably should get the GPU, because 40 milliseconds per sentence, I think this is faster than a movie frame at this point. Is it? Yeah, something like this. Okay, almost. Conclusions, at least. Replacing phrase-based SMT with NMT seems to incur no quality loss in terms of blur. In most cases, improvements, and in the case of Chinese, huge gains. You would, however, need to train on the GPU, I guess. Quality after 10 days of training mostly converged. Small gains were still possible, but probably not worth doing it in a deployment setting. If you want to win shared tasks, sure. If you want to just put your systems online, probably not. WLT-grade models can be deployed on commodity hardware. So basically, what people are using now to win shared tasks is something that anyone can use for their in-house translation system. CPU-bound translation speed is similar as phrase-based SMT for an in-house setup in this particular configuration. GPU-bound translation is much faster. Future work, in which we didn't tap at all, is determine the impact of model size. So do we actually need to have WMT-grade systems? Maybe we can just cut the hidden layer size in half and get 4 times faster translation by that. Maybe we are not losing translation quality at all, especially with the slightly weird United Nations corpus, which is very repetitive, and maybe there's not that much knowledge that needs to be encoded in large models anyway. Human evaluation in a real-world setting. We have blur, but we don't really know what that means. Maybe systems that have similar blur scores are actually much nicer for humans to run. There is some work going on at the United Nations now. They saw the paper, and we are thinking about starting an in-house evaluation, like hidden A/B testing, so that the in-house translators, of which they have, I think, hundreds of translators, would not know which system they are using, and we would collect data, post-editing effort over a couple of weeks and see what happens there. And a bonus slide in terms of deployment. While this was the presentation that you saw was a kind of a case study, this is now actually a real result. So we have deployed exactly the same system at the World Intellectual Property Organization, which is one of the United Nations agencies. And Chinese English, I think, is already live and accessible from the outside and the inside. So the translation service, the in-house translation service is using it for CAT, and the outside can use it to translate patents from Chinese into English on the website, on the Patent Scope website of WIPO. And an interesting comparison, WIPO always benchmarked the systems against Google, and they were usually quite proud that they were beating the phrase-based system of Google, although Google had a collaboration with the European Patent Office. So they do have lots of patent data in there. So that was blue at this point was the phrase-based WIPO system, red was the Google phrase-based system on a particular test set. And they would have become very worried by the performance of Google's neural system. So this is the general NMT, the GNMT system by Google. And this is really interesting, actually. So a general translation system can beat a domain-specific patent system trained exclusively on patent data and can beat it in terms of patent translation. But when we do the same thing with an in-house neural system, this happens. And we are seeing a gain of more than 10 blue points for French English, which I don't think I would ever see anywhere. This, I think, is roughly 30 million sentences of patent data for French English. I'm not surprised by Chinese, Japanese, or Korean, but that French English is actually possible, I wouldn't have thought that. And, well, this is quite a gap. I guess WIPO has a little bit of time now until Google can catch up with that. I think we would have to wait for the next big thing. And we are also working on a custom C++ training framework. So with toy models at the moment, we are 2 to 3 times faster on identical models. It's not quite done yet. I expect until the end of the year, I might be able to announce a Nematus version that should create compatible or identical models. I don't know yet how much faster it will be. I hope we can keep this 2 to 3 times faster factor or even more. Thank you very much.
Thank you very much. So, questions?
Hi, Marcin. Really impressive results. Go back to that last one on French. Have you So you said you don't really know what's going on there, but have you looked at anything in the output? Again, just blue scores without looking at distribution. Is it certain sentences that suddenly in patent domain went from being horrible to suddenly being done right? What's going on there?
That's happened from horrible to being done right. That happened for all the Asian languages. So there really for Japanese English, this 10 blue point difference is a difference between unreadable and really nice English. The comment from the head of the translation section in WIPO was, I can work with this. Well, before he was against MT, actually. For French English, we don't know yet. It looks a lot better. These are results from last week for French English, actually. So we didn't really do any analysis yet. But what is going to happen here as well, and this is not in the planning phase anymore, this is happening in deployment right now. We are also going to do A/B testing for this. So we will have probably tens or hundreds of thousands of segments A/B tested and posted it all with SMT and NMT. And I hope we will be able to make this public as well. And then we will know what's going on. At the moment, we are just happy about the blue scores because, well, even if we didn't do manual evaluation, 10 blue scores is probably not something you can argue with. So, there was another comment from the head of translation, though, that he would not give neural NT output to an unexperienced post-editor as compared to phrase-based because of the fluency bias and the adequacy problem. So the neural NT system might fool a person into thinking that this is a good translation while it actually has missed an important bit or something like that.
Other questions?
Yeah, you said that if you train the network twice as much, you gain a little bit more blur.
Yeah.
But wouldn't it be cheaper to train a second model for 1 week and use an ensemble with 2 different seeds? Because then you have the same.
Yeah, probably. But the problem is then you end up with an ensemble, and then you have half the translation speed.
Yeah, okay.
And also, I also kind of said that it's probably not worth to go into the second week at all in a deployment setting. I mean, do you really need 0.4 blue points when you already are around 60 or something like that? For a shared task, sure. For a setting that's actually going to, where you actually want to have your system online, I'd say just don't do it.
Do you have an explanation? You said when you merge the ensembles from the same training run, you get basically the same result as actually doing the ensemble. We tried it as well and it worked exactly as well for us. Do you have an explanation?
We've been thinking about that. The theory is that we are basically doing something like a weird SGD update over those models and smoothing. You can probably sit down and rewrite this arithmetic average into an SGD update mathematically. It must be smoothing at one point. And apart from that, I don't really know why it works. I mean, of course, it only works across a single training run, which kind of suggests that there's some SGD magic going on there. The problem is the perplexity increases. So this is, I think you did those experiments that the training algorithm doesn't like it at all. It goes immediately back to the previous blur scores. So blur goes up, perplexity goes up as well. So it's something weird. In terms of training, this model is in a parallel universe somewhere. It's not on the same plane of optimization anymore.
As your latency in your timing slides, you list Moses on there. Is that classic Moses, or is that the improved performance branch that
that was the exact system I was talking about. So the in-house system that they are using at the UN, there is an OSM in there, which slows things down quite a bit. The phrase table is pruned. Cube pruning limits are quite low. So I'd say it's probably faster than a very, very standard setup. It's probably, there could be a lot, I mean, just lose the OSM and you're probably 4 times faster immediately. We kept it because we were having up to 2 or 3 blur points improvement due to the OSM. Okay. I mean, we are seeing bleu scores of around 60. I don't know, at least for French English, I don't know how much space there is left for fantasy at this point. So it's probably still a lot better. I'll just say that as this person really correctly identified, you just need to be an experienced person to not start trusting this system too much, and just remember that it is still an automatic system. Ideally, I think, and this is probably something we'll work on, we should have some color coding. We should say, okay, in this area, take care. Maybe look at the source, because something might not be quite right. So I guess the interesting times for quality estimation are coming. Yeah. Yeah. That's why I'm very interested to see what happens in this evaluation experiment. We also have timestamps there, so we might be able to report on processing time. It will be a little bit unreliable, but for many, if you collect thousands or hundreds of thousands of segments, maybe we can extrapolate something.
Okay, so thank you very much. Let's thank the speaker again.
Hello. I'm going to present my work about factor neural machine translation architectures. I'm a PhD student in Lyon Lab in Le Mans in France. We work in the neural machine translation framework with a sequence-to-sequence model implemented in an encoder-decoder recurrent neural network. We input the source language, the encoder-decoder, and we output the target language using a softmax to get the probabilities, which has the size of the output vocabulary. So the NMT approach has some problems due to the softmax normalization, because it has a high computational cost. And this leads to a limitation of the vocabulary of the output that can generate unknown words. There are some solutions in the state of the art. Like the most common approach is the sort list, where we keep in the vocabulary the most frequent words, and the rest are mapped to unknown. It's simple, but it can generate many ANC tokens. Another approach is the structure output layer applied in language modeling, where we have a main sort list plus additional softmax with for words classified in subclasses. It can manage more vocabulary, but it's a more complex architecture. Another approach is the one of Jan last year, where they select the batches according to the vocabulary. So the softmax can be applied only in a subset of the output layer. The architecture remains the same, but there is a mismatch between train and test mode. And more recent approaches are the subword units extracted by the byte pair encoding done by Senrich, and the character level NMT. They are simple, no, they don't require external resources, and they don't generate ANC. But we don't have control on the output. We can generate incorrect words. BP is one of the main methods used currently. We saw it in here. But none of these methods are including the linguistics to solve this problem. We propose to use a factor word representation. It's based on the way humans learn how to construct inflected word forms. For example, from English, the lemma B, we have many inflected forms, and for other languages, highly inflected, like French. With the lemma et, we can have many more derived forms. All the person forms, number, and tenses. Some related factors words are the factor neural language model, where they add the factors in addition to the input, to the words. And also in neural machine translation, also SEMrush use the factors as additional information of the words in the input size of the neural network. Our method differs on the previous, that we use a factor level for training the model. We don't use the words. We use it in the output size of the neural network. For the rest of the presentation, I will present the factor MUMT architectures, the experiments, a qualitative analysis showing some translation examples, and I will end with the conclusions and future work. In the standard MUMT, we have as input the source words, the MUMT system, and as target the words. But in our system, factor MUMT, we have two outputs, where one is the lemma, and the other is the concatenation of the factors. For that, we use a morphological analyzer. For example, from the word in French, devient, we extract the lemma devenir, that is like the infinitive form. And the factors are the post-tagging verb, the present tense, the third person, no gender, and singular number. With this information, we can generate the surface form. And we keep the same size of the output of the words for the lemmas, and we add the second output with a small size for the factors. And with these two outputs, we can generate larger vocabulary. We are based on the MUMT model of the work of Badanao in 2014. That is a bidirectional encoder-decoder with attention mechanism. The hidden state is a conditional group where the inputs are the previous state, the context coming from the encoder, and the previous generated token, its projection. And the code is from the winter school done in Dublin in 2015 about deep learning for MT. We extended this code to generate the two outputs, one for the lemma and one for the factors. And they are generated synchronously. And we also forced to have the same sentence sequence length for the factors to have it equal to the lemma sequence length. For comparison, we also use the system of IRAT, multi-way multilingual, to have the lemma and factors as the output languages. Now I will present the experiments. We work with the pair of languages from English to French. With the IWSLT 15 corpus, we do a data selection to to extract the relevant sentences, and we filter out the long sentences. And we end with 2 million of sentences. We keep as previous words the size of the input vocabulary to 30K. And for the output, the word output and the lemma output size, also 30K. And the factors output size is 142. And with the 2 outputs, we can end up in 172K words for the factor NMT system. These are the settings for the neural network. We applied a severe weight initialization, clip, gradient clipping at a delta. For the first results, we compare the factor NMT system with the standard NMT system in word level. And we can see that we obtain better result in Meteor. We use in factor NMT system as feedback the lemma embedding generated in the previous time step. We see that the number of ANC tokens are reduced. And we compare also we evaluated the lemma and the factors outputs. And to compare it with the standard NMT system, we extracted from the output in word level with the morphological analyzer, the lemma, and the factors. And we obtain better score in these 2 outputs. We also compare it with the VPE the same way. We see that the VP doesn't generate ANC tokens, but it's not reflected in BLE and Meteor. Also, we have room to improve because we can use the ANC replacement to improve the results of the factor NMT, but it's not possible in VPE. About the multilingual approach, where we have the lemma and factors as output languages, we see that in lemma and factors level is working better than our, but when we combine the 2 streams to generate the words, the score is much lower. This is due to the asynchronization of the 2 streams. The last one is what we call chain model, where we have 2 standard NMT systems as a chain. The first system has as input the English words and output the French lemmas. The second system has as input the output of the previous system, and the output is the factors of French. And with the 2 outputs generated, we can combine them to get the words in French. We see that in the results that the lemma performs similar. The factors is very high, 90. This is due because the easy task from translating from the same language, French lemmas to French factors. But when we combine both to get the word level, it performs lower than the factor NMT system. This is due because the training of the 2 systems are separated. We also, observing the results, we would like to improve the factors blend, because if we compare it with multilingual, is 3 points below, and using this helping is pretty high. So, and also because it's a very small output size, just 142, 40 of blend is not a good result. So we made some experiments to try to improve this output. We wanted to use as feedback also the factors output. We first use as previous the lemma for feedback, because the lemma contains the main information of the word. And also we try to compare it with just the factors as feedback, just this one, not this. And we can observe in the results that the best result is the one for the lemma, using the lemma feedback, and for factors using just the factors feedback. But when we combine to generate the words, the lemma feedback works better, as we expected. Also, we try to use the sum of the two embeddings as feedback and the concatenation of them. And we see that the best solution is the concatenation of them. We see that the factors output has improved if we compare it with the previous one we had. But we don't observe big differences in word level. Also, due to the high score we saw from the lemma friends to factors friends, we explore another approach, giving the information from the lemma to the factors output. The first one is giving the previous generated lemma in the previous time step to the factors output. But this result didn't improve. Maybe because we are already passing the embedding to the hidden state, and this is also passed here. Another, the second one, the passing the current lemma, is working like we generate first the lemma, and this generated lemma is passed to the factors output. And this has an improvement in the factors output. And the lemma remains similar. In words, it's quite similar. And the last one is the second figure here, where we pass directly the previous generated factors to the factors output. And this improves also the factors output. But when we combine, we don't have much improvement. Another experiment that we did is the translation of the sentences according to the sentence length. For example, the first part is the sentences from 10 to 20 length, later 20 to 30, and so on. We compare the NMT system with the factor NMT system. We can observe that they have similar performance until sentence length 80, and after this, the FNMT system is working better. This might be due to the less sparsity of the lemma and factors space. There are less choices for translation. And here I am showing some examples. We can see that the NMTs, the standard NMT system versus the factor NMT system generates a lot of ANC tokens, but the factor NMT system can translate. In the first example, the length of, we just see a part of the sentence, but the sequence length is 90. These words in the reference, adapté and ligné, they are in the vocabulary, but due to the sentence length, the system couldn't generate them. This is in red, and later in purple, I put an example where the FNMT system is translating well, but because of the corpus that we have just one reference, is not reflected in blue. It's also a good translation, but it's different as the reference. And the NMT system generated ANC. The word in green, reparant, is not included in the NMT vocabulary, but is included in the lemma vocabulary, so we could generate it. And the last one is a name entity that we could generate also, and is not included in the standard NMT vocabulary. Also here we have another example comparing the factor NMT system without the dependency versus the factor NMT system with the current lemma dependency, where we generate first the lemma, and with this information we pass it to the factors output. We see that there was a problem here in the factors output. The factors is grown, but with the dependency we could generate it well. And yeah, this is a direct translation from the English, and this was a good translation, and it's like the reference. Another example comparing the factor NMT system with the BP is that, for example, here with bafflet in English is translated to buffet with BP, that this doesn't exist in French. But the factor NMT system translated to déconcerté, that is even a better translation than the reference. But the blue cannot reflect this. And for the conclusions, we have a factor NMT system based on linguistic a priori knowledge. There are some constraints that requires up to date linguistic resources, and it's difficult to find them in low resources languages. And it has a slight increase of the model complexity because we add the two outputs. But we have pros. We can manage 6 times bigger vocabulary. We can generate new words that are not included in the shortlist. It performs better than other state-of-the-art systems. We reduce the generation of ANC tokens. We produce only correct words compared to the subwords system. And for future work, we would like to include the factors also in the input size. And this will decrease the number of ANC also in the source. And is motivated by the work of Senrich of this year. And we would like to extend the factors to n. Now we are using the concatenation, but we would like to use different inputs for each one and different outputs for each factor. Yeah, we can include more factors if we want. And this will allow us to generate more the system and produce more sync words forms. And we would like also to apply to highly inflected languages as Arabic. Yeah. And thanks for your attention. And you are invited in Le Monde, France. Yeah. Thank you.
Thank you very much. So, questions? Over there. No, over there.
Hi, thanks for the talk. So you've shown some improvement in both lemma and factor, but not at the word level. I think there was in some tables. And
We need to run more experiments.
But
I think we
how
have
do
room to
you-
improvement.
how do you generate the words again? It's like
Ah,
a
it's,
rule-based.
Yeah, I have another extra slide that I can. In the beams, well, we produce the two systems, and in the beam search we generate like the best options. For example, here in this figure we have 3 hypotheses for like beam size 3, and we generate 3 options for each one, and we combine them, keeping the most probable ones.
But this is
So
only for
we end up for each hypothesis to 3, and we combine these 3 again to get the 3. So we stay in the beam size.
But this is just lemmas and the factor. But then you evaluate on the word itself.
Yes,
right? Because
later we also use the morphological analyzer to get the word from with the lemma and factors.
So maybe that's the problem why you don't see an improvement? I mean, you've improved the lemma and the factor, but then when you generate.
But we have the information to generate the word, so it shouldn't be a problem. If, for example, here in the example I put, we have all the information here to generate this word, just with the lemma and the factors. So, I saw some few cases in French that there are like 2 forms to generate the same thing, like some verb forms that they can write them in 2 ways, but both are correct. Just that we have just one reference, so sometimes the blade doesn't work, and maybe that's why in Meteor I have better results. Yeah. So we can also apply it in another corpus with several references and evaluate. We would like to also do a human evaluation. Yeah, but this shouldn't. We have all the information to recover to the world.